Yeah,
And I would actually use the poll this time.
I will do it this time.
Ways, and I'm like, this is making it harder to schedule. But truthfully, from what I'm hearing, they might have suspended the program anyway, so I don't know like if we're even getting money. Like,
Okay. Yeah.
I guess.
What's up? All right, folks. The time is 9.
There will be pizza in an hour, just letting you all know.
So we have talked about what it means to be a fluid. And now we get to finally talk about what a fluid does. Seems like lots of folks are having trouble on problem 3. Okay, so we will maybe do that at the beginning of the office hours that start right after class. Okay. In order to talk about fluid dynamics, we really have to talk about like kinematics. And so that's what we started off by doing on Monday. And we were talking just about coordinate systems, more or less. And we were talking very generally about how we're going to do math in this moving coordinate system. Because the important thing to keep in mind is there's 2 ways to view any flow. And you can view that flow along with the particles, or you can do it with respect to a fixed time, or sorry, a fixed space, right? And we have to be able to go between the 2. We have to have some form that allows us to transform from one coordinate system into the other, because one is not better than the other. Does that make sense? Okay. So of course here you have some very, very advanced fluid dynamics. Okay. So you may not think about this very frequently. An Oreo. Everyone familiar with an Oreo? How do you eat an Oreo? Take it apart and then what happens? You lick the white part and then you eat the cookie. Very good. And how do you separate the 2 halves of the Oreo? You just pull. Oh, serial killer! Oh my god. Okay, so why do you rotate them? They're sticky. So the first thing you do is you rotate both sides of the Oreo, and that does something to the Oreo cream filling that allows you to pop off the top. That wouldn't have happened if you didn't do the rotation. Okay. And in fact, that's what they did here in the lab. So this is fluid dynamics of what happens when you have a fixed end here at the bottom, and on the top, they're going to rotate the top of the Oreo. So you have wafer, cream, wafer. Now we all know that wafers are solid, but what is the cream? Like a glue. Paste. Okay, a paste. So what state of matter is the cream?
The super viscous liquid.
Ah, okay. So just because we're not familiar with how the viscosities work, right? Like how sticky it is, we may consider it as like halfway between a solid and a fluid. But it has fluid properties. And in fact, it is a fluid. And we'll see that today. The reason that it's a fluid is because it does this. Now, this doesn't make sense yet, but I'm going to demonstrate when we talk about stresses and strains. It communicates the strain non-linearly, or throughout the cookie. So when you rotate the 2, right? If the thing was one solid piece, the cookie in your other hand would move. Right? So we're solid all the way through. The whole cookie would rotate. Because you can't take a Chips Ahoy cookie and rotate the top of it. Right? But you can take an Oreo because it's solid, fluid, solid. And because of this, there's obviously shearing at the very top. And that shearing overcomes the gravity, or not gravity, sorry, the intermolecular forces that are bonding the cream to the solid. And that allows you to remove it. Okay? So we're gonna talk about stresses today, and I can guarantee that this will be the most confusing part of learning about fluids, okay? So be prepared to not get it, and that's okay, okay? We're gonna get better at understanding it with time. So let's go back to this idea of the Galilean transformations, okay? If I throw a ball, right, and let's say I'm throwing the ball to Zori, she catches the ball. Okay, we typically do that with kinematic motions, and you can describe the motion. You got gravity down, some initial velocity, right? You could, for example, change reference frames. You could be in Zori's reference frame, right? And you could see the ball come towards you, or you could be in the ball's reference frame, and you could be, say, moving. Right, maybe you're accelerating at the beginning as you slow it, or as the ball slows down, gets to its apex, and then comes back down, whatever you want, right? And we have these Galilean transformations. You know, we have something like, if you imagine some reference frame, and I'm just drawing it in 2 dimensions here, x and y, okay? And let's say we're moving to the right with some velocity v, then you would have a different reference frame, x prime and y prime. How are these related?
Zero velocity, right?
Yeah, one of them has 0 velocity, so you're right, but this v is only in the x direction. So how does y prime and y, how do they relate? Yeah, but you can see it. You can see it with your elbows.
Oh, space.
Yeah, so how do I relate these two, y and y? If a particle was here in this frame, and then I move to the right, where is it in the new frame?
Yes,
In y.
y plus whatever distance moved equals y prime.
Does x distance affect y? No, good. So in fact, if I look, it's still y equals y prime. Okay, good. That's the first part. So now x is the tricky part. So now we have some relationship between x and something with x prime, and maybe something else here, right? What would be the extra thing? Which is? Which is which number?
Vx times t.
Vx times t, correct. Good. Here's another one. Now we have to ask, you said t, there's t in both frames. T equals what to t prime? So t exists, it's not drawn on the board here.
That's where we
No. So you're absolutely correct if we are thinking about relativity. But we are simple folk thinking about fluids on a rainy day. So T here and T here, how do they relate?
So it's like a path that if t in the beginning is 0, then the next one would be like 2. 1 or 2 seconds.
Sure, but think about being in both of these, right? If I throw the ball, okay,
Oh,
so it's my clock compared to the clock on the ball. How do they relate?
start with the same.
Start at the same time? They should be?
T.
Exactly. Okay. This is really important. These are the Galilean transformations. When you think about kinematics, this is all that he thought about, right? He was just talking about the ability for stuff to move and the recognition that motion in one direction may not affect those in the orthogonal direction. So if the reference frame moves left to right, then up down is not affected and time is not affected. to your point, Trinity, the brilliance of Einstein was to realize that if you move so fast that you approach the speed of light, then that's no longer true with respect to. Does that make sense? Okay. Okay, so in a fluid, we have these kinematic equations, but it's not so simple anymore because you're not following one particle, you're following many particles, right? And we have these things. We call this thing the total derivative. Do you remember that? How do I write the total derivative?
Capital D dt,
Okay, is
del F dot U,
del F
and that quantity dot U. Plus partial T,
Okay. Is that fair? Let's be a little careful here, right? So this is the dot. And those are vectors. Okay. So now let me ask you, what happens when we transform the velocity? Let me write this again. If F is the velocity, how would I write this? Left side first. Of you, good.
del U. Quantity dotted with U again. Plus partial T U.
Is that okay? What? What do you mean? What do you mean you don't have?
I have to remember, but I don't know, like units for the first one. Del U dot U.
Del U dot U, yeah, that's a good question, right? Okay, so, we're gonna. You can write this. Okay. As U dot del of U. Where that is. Yeah, so what we did here, okay? So what is the direction of U? Right, this is dotted into U, right? So that's the directionality. And then the del, U dotted into the del. Does that make sense? We can show this in more detail if we want, during the break. The important part here is, let's imagine what happens in a transformation. Okay? So we already set up here that x equals x prime plus vt, right? The v here is of the reference frame moving itself, not of things in the fluid, right? But you could then write that u in some reference frame would be big U plus U prime. Is that fair? So we can just transform the relationship between them. And this one's okay up here. It's going to be the same. This will allow us to say that the total derivative in this unmoving frame is going to be equal to the derivative in the moving frame. Now let's just double check intellectually that that should make sense before we show it. Okay. So let's think about what the definition of the total derivative is.
Where it tells you about. What, the flow caused the density to change, and what has to do with time?
Good. So you have the steady term, or the unsteady term, however you want to call it, and the. There's a special word. This is the advective term. So this one is of or having to do with the motion of the fluid, and this is of or having to do with the steadiness. Okay, so let's have a look at this example here. Here I have a ball, and I have fluid going around the ball. And on the top, I said that this was steady or unsteady? Steady, right? So you can follow some particle, and let's say we pick a point here. The particle's going through that point, steady, time derivative equal to 0. But if I choose a similar point here, with now the ball moving, the object becomes unsteady. Okay. So if I tell you that du prime dt is equal to du dt, how is that possible?
Because the vector part is less in the one where it's not steady.
Good. This is really important. What we're saying here is as we move between coordinate systems, we trade in the total derivative values like advection become unsteadiness, and unsteadiness becomes advection, depending on which direction you're going for a specific fluid. Does that make sense? Okay. I'm gonna leave this up here, and maybe we come back to it in a homework. I don't know if folks feel like they'll feel more comfortable doing it themselves. But here we're really using vector relations in order to show that this is true. And in particular, if you haven't brushed up on the Galilean transformations, maybe we can assign a problem that looks like that. Okay. Okay, so now we get into everyone's really interested to know about the Oreo, right? Is that why you came to class today? Okay. So let's think about the ways that a fluid parcel, and remember this is not an actual object with walls, but this is the concept of a parcel, right? And there's different ways that fluids can deform. So what do I mean by deform? Change shape, exactly correct, right? Okay, ready? So let's do, we have to use our imagination. Anyone not able to visualize stuff in their head? So this is like a aphantasia, I think it's called. It's like where you try to think of an apple and you can't see an apple. So that will make this harder. So if no one has aphantasia, this will be easier. It's still possible, but we just have to make more drawings and I have to use my hand more. So I have a box, okay? How can I deform the box? Excuse me? Squish it. Okay, so let's be a little bit more careful there because your hands did this. So I want to do that each one individually. So let's do this one first. Okay, that's one squish. That's another squish. Right? Those are two separate squishes that we have to keep track of. Okay, what other ways? What? Ah, the opposite. So you can pull it out. Good. Is that it? That's only 3 so far. Push, push, pull. It's fluid. Oh, whoa, don't look at the screen. All right, cheater, pumpkin eater. Let's go back.
I was just like, I don't know.
Go back, damn it. Just giving it away, okay. All right, yeah, so you can deform a fluid, right? Let's say our box. See our box is like,
Flash.
it's like flashing on the water. Okay, let's say our box of fluids like this. That is a different box, right? Who would agree? That's a different box. That's a different box. That's it. Okay, rotation is a deformation. Okay, anything else? So it's 3 different types.
Is rotation only allowed because it's fluid?
No, I just rotated a solid.
Well, I would consider that the same because it's solid.
So you would consider the iPhone the same. That's true. But think about if I draw the outline of a box with the locations of the box, as I rotate it, those are new locations, right? So going from here to here, this is O to O prime or something, right? Okay. So we have 1, we have 2, we have 3, we have 4. Okay, that could be another form of a rotation. Good. 5.
Should I do it the other way? Because you went to the side, I think.
Ah, okay, 6. Gotta get the other one. 6. You're missing the coolest one now.
This,
7, 8.
What?
like, spin it.
Yeah, that's a rotation too.
Oh.
Yeah, so this rotation, those are 3 rotation axes. Good. What do you mean flip? Like that? That looks like a rotation to me.
Fine. The front and the back,
The front and the back like that?
because you.
No, it's a 2D box.
Oh,
2D
you
box.
do, okay.
Yeah, you're right. We can do the front and the back, and we can do the side there. Yeah, but we're not gonna get there yet. Compression, yeah, compression is squishing. Yeah, so my fingers came. Oh, I guess they could get shorter. Oh, look at that. I'm fucking smart, right? So that's compression. And that would be expansion. Come on, folks, do your hands like this. You will get it so quick.
We're looking for another thing.
Put both of them. You've never done this before? All right. Finger guns 1, finger guns 2. What's the other thing I can do?
Like diagonally squish it.
Ah, diagonally squish the box. Okay, so that's a deformation, isn't it? Right? That's not the same box. So that's a deformation and that's a deformation. And those are 2 different deformations, right? What?
Not the same when compressing
It doesn't look like this, does it? Sorry, hold on. It doesn't look like that, does it? It's a new box. Right? This box, you know, and I think your point is, well, you could say, well, that kind of looks like maybe a push and a rotate. Right? And so the question, this is a very, very good one, is Zori's point right? Can we mathematically show that this is equivalent to maybe this and a rotation or something? Okay, you'll see why. It's really cool. Okay, where'd I go? So we did it. We thought about all the ways that we can deform a parcel, and now we can call them different things. Okay, so we have stresses, and that's not just how we feel every day. We have strains, and that's not, you know, the impact of going to shows on our budget. And we have rotations. That's not our types, right? Okay, so here's the definition of each. Stress. This is the transfer of velocity along a differential gradient. What does that mean?
Whatever. What was causing the stress, that velocity moves from that to the gradient fluid.
Say that again. So what was causing the stress causes.
The velocity of the fluid to change.
Yes, okay, so what you're saying there is that something that's maybe making a change is transporting that change into the velocity of the fluid, is that correct? Did I understand that properly? Good. Yeah, and in fact, that's the image that I showed at the beginning, but I didn't show you that I showed it. So let's go back to our idea of, here's our wafer cookie. Okay. And the fluid that's in contact with the wafer at the bottom has a velocity of, so this is V equals 0. And up here, the velocity equals something, non-zero. Okay, let's call it 10. So big. And up here, big velocity. So if it were solid, to go back to the idea of the famous Amos cookie, the bottom would just move. Right? The whole thing would move as one rigid object. Or it would break. That also happens. That's all things is the forces can't hold together the body and it snaps. Right? But for fluid, it allows deformation by transporting the velocity through the fluid. Now, how far you transport the velocity varies from fluid to fluid. Okay? But right here, right next to it, let's say I have a little point. How fast is it moving? Pretty fast. Maybe a little bit slower, right? And then maybe right here at another point, a little bit slower. Here, a little bit slower. Here, a little bit slower. Here, a little bit slower. And maybe it doesn't propagate all the way through, and all of these dots are different. Does that make sense? Okay. So what this is doing is this is showing you there is a vertical gradient of what property? The velocity. Very good. Okay. So this is the transfer of velocity along a vertical or differential gradient. So stresses, if you want to think about your fluid, okay. Let's go back into the metaphorical pool, and it's a summer day, and you're trying to splash your cousin. How do you do it? You smack the water. Good. And the smacking the water does what? Yeah, it stresses it. So you are able to transfer velocity into the fluid. And the velocity in the fluid starts to match your hand and gets flying into your cousin's face. Good. All right. So that's stress. Strain. Can you strain water? Compression and distortion. This is a little harder. And the word distortion and deformation are gonna sit in our minds weird until we see them worked out in paper. But typically this is quite hard for us to do. This would be like compressing the water or rarefying. So I can't pull water apart with my hands, nor can I compress it. Okay, so we don't have a lot of first-hand experience with this, but we understand this concept pretty well because we understand the idea of putting things under pressure, like a piston, right? So pressing down on a gas, making it have some higher temperature or higher pressure in there, such that you deform the container and there is some strength.
So is that like the hydraulic stuff?
Yeah, hydraulics are due entirely to the fact that you can use the properties of the fluid in order to, for example, you can stop a car. A car weighs 2,000 pounds. If you use your hands to try to stop the car, you will get run over. But for some reason, if you just do this with your foot, you can stop a 2,000-pound car. And that's through the hydraulic strains. Okay, and this one's straightforward. We don't need to explain this one. We rotate the object. Okay. Yeah, so we'll talk in more detail about these ones here when we're thinking about the velocity gradients as a whole. Let's first talk about the strain terms. I think those are gonna be the easiest to understand and you're gonna have the most familiarity with the mathematics there. I have an answer.
Do you say piloting and verifying? Is that like synonymous with one of these words?
Where?
Pilot right there.
Yeah. So piling up, you want to think about a fluid channel. Right, and so we try to start thinking in 2 dimensions, okay? And so I have some fluid that's coming in like that. And you know, you maybe have complete control over what's happening here. So maybe the fluid is coming in at some velocity u, and it's compressible. So that means that its density is allowed to change. And it's going through the flow, and right here at this part, it starts to pile up. So maybe there's like, I'll do like a little bit like this. And that's how much flow there is. But over here, there's more. That would be piling up. And then as it leaves again, that would be rarefication. Rarefication just means the spreading out of a gas or fluid. Okay. What's an example of rarefication that you don't know that you use every day? What? No, breathing? Hopefully not. So in fact, refrigerator systems use something called Freon. Very dangerous, very toxic. Don't breathe it in. It's a closed system. And what it does is it uses the rarefaction and compression of a gas called Freon, to suck away heat. One of those processes is a heat sink. Okay, so by rapidly changing the volume of the gas, either by compressing it or by expanding it, it will grab heat from whatever is nearby. And it just so happens that if you go home tonight and you look at the back of your refrigerator, you'll see metal coils back and forth and back and forth and back and forth. Same thing works on a radiator, right? You have very hot fluid and it goes through these coils. Something happens in those coils and it's able to emit heat, right? Refrigerator works the opposite direction. It grabs heat and puts it in the Freon and pushes it out the back of the refrigerator. So if you've ever thought to yourself, and this is a thermodynamics question, if it's a really hot day, and you're like, oh, I know what I'll do. I'll just open up the fridge. Is that a good idea? What?
That's adding more heat.
It's adding more heat. Good. Because as you open the fridge, the back of the refrigerator is still in your house. So unless the back of that refrigerator points outside of the home, right? This is why air conditioner units, they have one side that's cold and on the one in the window, right? The side that's cold, that's inside the house. The side that's hot, that's outside the house. So what you're doing, you're taking air, putting it in the air conditioning, cooling it, and spitting hot air one direction and cold air the other. Okay, that process is rarefication or piling up compression. That make sense? How are we feeling about these concepts so far? I know we're moving a lot slower now, but hopefully this is like. All right. Why is this not like me today? What did I do? Let's talk about the strain terms. So we're going to write something called the strain tensor. Okay. So we can start with this thing, del u del x. Okay, and these are generalized coordinates. So when I say u, I'm actually going to be able to add a subscript. And I'm going to add the subscript I. and I'm gonna make it different than the one that I add for j. Now, what does ui mean? What should you see that as? What? What does ui mean? Like how it, in your mind, when you see the letters ui, what should you think when we're talking about tensors, vectors? Good. So yeah, so we might get tripped up into thinking that it's the initial, but it's actually the ith component. So in a three-dimensional system, ui represents what?
We use it for X, but it's, yeah, that X component I can.
Okay, so it represents a pair or a triplet, ux we don't need I. uy uz. So the only reason we don't need I hat is because I'm not writing them in vector format such that they're plus, I'm writing them in a triplet. So if I write them in a triplet, then I know that the first position should be the x position. Good, and how do I write x? What does xj mean in the same triplet form?
That's of X.
X, y, z. That make sense? Okay, so now we get to throw in something that you may or may not be familiar with if you haven't taken either Math Methods 2 or E&M 2, and that is tensor notation. Oh, okay, so what this means is that I have two indices, and typically what we're going to try and do is we're going to have them represent all of the potential combinations. Okay. So here, I'm going to write something that says S I J plus 1/2 R I J. Okay. This is the strain rate tensor. Okay. And this R, very easily written, is the rotation tensor. So what's a tensor? Good, yeah, it's essentially a matrix in more than one dimensions, right? And so let's say I have some arbitrary tensor. Let's say it's A, I, J. Okay, how would I write this in matrix format if it's a 3x3? So you need big old parentheses. A sub 1, 1. Which way? Where? A sub 1, 2. Okay, now we're getting it, right? And then what's the next one? Good. And I'm going to finish the rest of them so we don't have to. Okay. And this one? Okay, we're familiar with that? Okay, so we're just using the indices here. And all I'm going to say is that for a given DUI dxj, that happens to be equal to the strain rate tensor of ij, matching this I and this j, plus 1/2 Rij, matching this I with this j. Does that make sense? So therefore, we could describe every single term, right? Whether it's d, u, x, d, x, right? What would I say here? It was I and j. J is X. Does that make sense?
So if you just don't put it, you just say this.
Well, you know, because hold on. Let's try a different one. I'm simplifying, maybe I'm simplifying too much. I could do X, Z. Now you don't have a problem with it, right? Okay, but I'm simplifying it by saying that instead of writing XZ, which sounds insane, that's okay too. Does that make sense? Because that's the intuitive one. But what you really are saying when you say Z is XZ, right? And so we've just simplified it. So let's do one more just to make sure that we understand this notation. Okay. This is the very good. Okay. Okay. So that's the first thing. This is equation 311. And you're saying, great, you've said nothing and you've created two things that suck, right? So now let's define those two things. And they do suck, but they're going to suck differently. Okay. The first one is this Sij. Sij is equal to 1/2 du I dxj plus duj dxi. And Rij is equal to the difference between dui dxj and duj dxi. Whew, those are weird, right? Okay. Anyone have an intuitive sense for what we've written? Okay. Okay, I can see that a little bit. So there is, let's start first with the strain tensor. Let's take the SII components. So if I and J are the same, and it's I here, what happens to this? One is DUI over DXI, right? And the second one? Over DXI. Good, that's the same thing twice, right? So that's just equal to DUI over DXI. So now let's understand what we're saying. DUI. How does the velocity, let's take an example, let's take X. How does the velocity in X change with respect to X? So if I squish the box, right, then I'm changing the flow in the direction that I'm squishing. That's a squish. Do you see? That's the mathematical definition of squish. DUI over DXI. Think about rarefication. As I pull the box away in the direction of the motion, right? It's the opposite. It'll be a negative squish, but it'll still be, right, the same process. Okay. So we say that SII defines the lengthening or compression of the fluid element. And now we can think of a particle. So Sij talks about the rate at which I and J fluid elements are headed towards each other. Okay? So let's imagine now, let's take two directions. Let's take the velocity, or sorry, let's take I equals X and J equals Y. Okay? So here I have this one. This is saying, how is the velocity in X changing with respect to Y? Does that have to do with the compression? No, it can't. Because in a compression, nothing's changing. Okay. So what's this one then? What is this one? And we had all these things that we did. Let's remember them all. We had this. We had this. What's the deformation that I'm doing here? Yeah, that's what we were talking about in the slide.
The first one.
The push one, right? Because here's what we're doing is I am changing the velocity in that direction as a function of this direction, right? So as I deform the box, that is a totally different one, right? So this is our strain here, right? Or our stress, I should say. Strain and stress we're going to use interchangeably when I'm not being careful. And the rotation tensor is very carefully constructed such that these two pieces, they're going to be the difference of one another. And you'll see when we start to use it, that describes the rotation itself. The whole box just rotates. Okay? So let's have a look at this mathematically. Here's this box. Here's that length A and the length B, and it's moving with velocity u1. Okay? Over some distance delta x1. Okay? And here, sometime later, u1 times dt, right? We have lengthened the box. We've made the physical box longer. And you will see that the only way that we could have done that was by adding, okay, u1 times dt, that's the distance, plus this differential and the difference in x, right? So this is how we're relating the size of the fluid parcel in its change. Okay. Okay. Let's see if we could use this. Oh gosh. Here's a challenge for you. On a piece of paper, or you can work with a friend, but only one friend. I want you to look at this box that I created. And I want you to write down for yourself all the ways in which the fluid parcel on the left here becomes the fluid parcel on the right. What's that? I don't know, you tell me everything that I did from the parcel on the left to the parcel on the right. And not with math. Yeah, just with words.
For we given X, so we think about we can think of it like you explicitly, the velocity while X is the dimensions. That's it.
What do we got? Let's do one at a time. So you said compress? What do you mean compress? So we got, I need to be sort of specific here so I can sort of say, so I can understand you're saying what I think you're saying. So here's my box. Which way are you compressing it, in X or Y? Oh, so you're doing this. Okay, which one are you bringing in? You're bringing both X and Y. Good. That's one version, right? That's a form of a deformation. Okay, how did it get over there? Good, so I translated over here, now it's over here. And I translated it up. Good. Is there a rotation? Not in the version she did. Right? Is that the only way to have done it? Good. Go ahead. Okay, so what do you mean the opposite way? So now we move over. Oh,
The top corner, right?
Yeah.
sorry, say this, like this?
Top right corner, you move it that way. And then you-
The top right corner,
Push it
okay?
a bit. A bit,
Flip it.
or rotate it.
This is still the same object. If I do this, it's still the same
Oh,
object.
you're right.
Okay, so that wasn't it. You're so close, you're almost there.
You're asking us to find one where we have to rotate it?
Yeah,
So like instead of squeezing it from in those directions, what if you pull it from those other two directions?
well then it just gets bigger, right?
No, like if you pull it from those other two diagonals? Wouldn't,
Other two, like this?
yeah, cause like if you pull this side, that's naturally gonna, the other one's gonna cave in, you know?
Okay, so that's a compression. Anytime that the angle gets closer, we call that compressing. Regardless of whether or not, these angles got wider. Because if these angles here go together, that's a compression. So the only way to widen it would be to do that, right? But then the question is do you keep that point over there? Or do these go out? Because if they go out to the right, if this point doesn't come in, right, then that's an expansion. Does the total area that's enclosed in this shape get bigger or smaller? So the question is this area the same as that area? Is it? What do you mean you hope so? Oh my god. Dios mío. Okay, this is the same length?
Two triangles.
Yeah, okay, let's go to the extreme. Okay, let's go to the extreme. Is this the same area as this? No, it's not. Come on now. You gotta see it. Does it make sense why? But let's think about the opposite one, right? That's clearly bigger, right? So even though this angle got bigger and these angles got smaller, because we didn't let this move in, right? Then it would have been an expansion. Okay, just a little trickery on a Wednesday morning. So now the last piece of trickery, what is the other transformation I can use to go from point A to point B? Or location 1 to location 2. So you did the compression, I like the compression, now I want you to use a rotation.
Right.
What are you talking about, right? Why do you want to move other walls?
Because how else are you gonna rotate?
Because
If
then
you,
you have it pointed that way.
press it that way, then you have to rotate.
Okay, ready? You ready? You ready? Okay, squish. Move. Up. Rotate.
Oh
Oh, that's so stupid, Grismon. But do you see that they're mathematically equivalent? Okay, you're right. They are dumb. But I just want to drive home this point that some rotations look like squishes and some squishes look like rotations, right? So there is some ambiguity there in the mathematics. Does that mean that we could not do fluids? No, of course we're gonna be able to get around. Cool, we like that idea? That fuck you up too much or not? A little bit. Okay. Let's talk about rotation. Okay. That's a lot of words. Okay. Let's talk about Rij. So Rij, I claimed, was the rotation tensor. Like that. Right? And I showed you some, what did I say it was? It was like the differential of u with respect to x or something like that, and then minus something else. Okay. So if you are incredibly like locked in, you would have immediately been like, that's the curl of the velocity. Now, I don't expect that you're incredibly locked in because maybe we've never even thought about what the curl of the velocity means. Okay, so let's first think about this idea of what we call vorticity. Okay, I'm going to add a new word and then we're going to define it here. This thing, that's not a W, I wrote it like Greek style, so think of it Greek style. This is called the vorticity, and it's defined as the curl of the velocity. It is a vector, and these are vectors. So let me ask you a question. What does curl mean?
Kind of like in PNM where it's kind of like spirals out of one place. So that's kind of.
Okay, I like some of the words there. Spiral out of one place. I'm hearing, and I don't know if this is what you're saying, I'm hearing like something coming, like an emanating from there. Is that what you mean? Or do you just mean that there are differences?
I was thinking more like a field coming out of like a sphere, so it's kind of like expanding
Okay,
as it goes through space.
okay. I heard rotation, I hear like a field expansion. So we haven't quite talked about the field part of this yet. This is a property of a vector field, that's true. So this is the velocity field. What we're really interested in here is how it's changing perpendicular to the velocity. So let me show you what I mean by that. So maybe this will help. Here's my box. Okay. The velocity is the same, and it's all going up and to the right. What's the curl? So your hand doing this, right hand rule, that's great. That's a good instinct for the cross product. But what we're talking about here is the gradient, how it's changing perpendicular to the motion. Is there changes perpendicular to the motion? No, it's the same velocity vector. And here's the thing, the velocity vector is going that way. I'm asking about changes going that way. They look the same. I mean, it's true that's the edge of the box and you can't see past it, but the same, I tried to just draw the same size vector. So therefore, del cross u here would be 0. And not surprisingly, this flow is moving up and to the right does it look like it has rotation in it? No. If I put a little ball here or a boat or a little child in a pool floaty, they would just go straight. By definition, straight is not rotation, right? Okay, so this concept here is the vorticity. How is the thing vorticitating? I'm not saying that. Okay. Let's try another one. Okay. So Daniel, you were talking about like field lines, and we're gonna not necessarily come to that, but we'll see something similar to that here. So let's try. Maybe you're familiar with bathtub. Okay. And after the bathtub, you pull the plug and the water goes around a drain. Okay. So let's say you have here the dot and you have the water going around the drain. And how does it move closer to the drain? Faster. And farther away, it moves slower. Now this one's a little tricky because we're going to need to use radial and azimuthal components. Which direction is the velocity? Yeah, azimuthal, right? This way. Good. So now let's compare the azimuthal direction to the direction that we want to take the change in, which is in the radial direction. Is there change in the radial direction? What? It's decreasing, yeah, it's decreasing as you go up. Good. So this is not equal to 0. Ah. So this thing, the bathtub, has vorticity. We like that? And here's where I'm really going to fuck you up. Okay? What about a CD player? Now you say to me, here's mine. A CD player that's clearly rotating, right? Does a CD player have vorticity? You know what a CD player is? Okay. Let's take the CD player. Here I have some velocity that goes this way. But now as I go out, right? The velocity vectors have to get bigger because it's in solid body. Could I construct something that was rotating that didn't have vorticity? Yeah. We've just thought about one that decreases as it goes away. Now we think about one that increases as it goes away. We could have one that is constant, right? So you could construct some fluid flow, and maybe this is unrealistic. We'll talk about it in a little bit. That looks like this, right? And that would have 0 vorticity. We like this idea of vorticity, even if we don't necessarily have like a oh god, did this quit? Oh god, I never shared this. Did I share this? Well, sorry folks who are watching online if I think Zoom just ended. It's fucking useless. So the rotation is the rotation tensor, I should say, is the curl of the velocity. It's this thing called the vorticity. And now let me show you what it actually looks like. So we write it as this beautiful, very normal letter called the Levi-Civicz tensor. It's Levi-Civicz tensor, but I like calling it the Levi-Civicz tensor because Civicz is better. But it's not the name of the dude.
There.
Yeah, so negative, it's basically a little e essentially. And then it's ijk, and then it's omega k. Now, for folks who don't love tensors, when I have two of the same indices, that means that you do the sum over each of the components of that tensor. So what I mean by that, and I'll show you in a few seconds. K here is a summed index. So you would do all of k equals x, and then all of k equals y, and then all of k equals z, and you would add all three of those components together to get the ij component. Okay. What does this look like when you write it out? Well, it's actually quite easy. It's a 3x3. And it's a 3x3 that has zeros on the diagonal. And it has minus omega 3 here, omega 2, omega 1, omega 1 down here, minus omega 2, and omega 3. Okay. You're saying to yourself, what the fuck is this guy writing? Well, we claimed over here that omega is del cross U. So this has three components. Okay. So first tell me what the first component, generally speaking, omega 1 is. Okay, so omega 1 or omega, the vector is comprised of omega 1, omega 2, omega 3. Okay? So show me what omega 1 is. Let's go back to this definition here, right? So if this, and we can think of this in terms of x, does that make it easier if we think of it in terms of x? So if this is x, by the right-hand rule, how do we get the x out of this cross product?
Cross Y and Z.
You have to cross to y and z. And is that the correct order, y and z?
Yes.
So y cross z gives you x? Okay. So then you're telling me that this one here is del u z del y, right? Because that's y and z. Gives you x, y, z. Gives you x. We like that? Are we done? No, because we can actually use the fact that this can be z and this can be y, right? But what do you get when you flip them? A negative. So I can also have here minus del u y del z. Right? You just look back in your notes. At R, when I wrote R I J the first time, like 2 slides ago, you'll see that that is the form. Right? It's d u I d j minus d j u j d I. That's the same thing. Right? So all we've done is we've created a meaning for that thing that we wrote in the original rotation tensor. Okay? And vorticity here is a measure of the spinniness, more or less, of the object. So obviously there's this nice time in the idea of the rotation. Okay, so we call a fluid is irrotational if
W zero.
Exactly, we call it omega, but yeah, it's exactly right. Perfect. If the vorticity is zero, the thing is irrotation. Okay? Why is it that the diagonals are zero? What?
The symmetry.
Yes, yeah, so the symmetry of the matrix, exactly right. It's an anti-symmetric matrix, very good. But intellectual, or sorry, not intellectually, intuitively, what do the diagonals represent?
Um,
Let's go back to the definition. Okay. Can I do x cross ux? No. And that's what it's asking me to do in the first diagonal. Right? So by definition, the vorticity of the first diagonal is zero. Right? And in fact, when we write it out this way, right? If I were to do dux dx minus dux dx,
um,
you'd also get it to be zero, right? Okay. Is that okay? I know it's weird. Is that okay? So if we have an irrotational fluid, we can find a scalar potential. And from that scalar potential, it's very easy to describe the fluid. We'll talk about that in detail. Running low on time here, but are you familiar with like Stokes' theorem? Converting from a potential to, using the gradient integral over a sphere, for example. If you can draw, if this is true, and it's a big if, right? If we can find the fluid velocity u, which is written as the gradient of some scalar function phi, right? Because of irrotationality, then you can solve these equations to get something called the circulation, and you get thing like this called the circulation, which is over this closed contour u dot, and this is just the surface. Or another way of saying it is that over some area, let's say a sphere or a circle, the vorticity dotted into some normal. This is super helpful because when you have an irrotational fluid and you want to simulate it, say on a computer, you can use the circulation formula as opposed to following every single parcel. Right? Because one parcel lumps into another parcel, so now you have a way of tying the whole fluid together using just mathematical properties. Okay. We have more, but we're out of time for the first section here. So maybe we need a mind break and we can mainline some coffee and then come back in 15 if people want to. Okay. I'm just going to pause. The next question, I suppose, is does any of this look familiar? What? What do you mean? None of this looks familiar. This all looks like bullshit, Grismani. Okay, so here's Max. Oh, fuck. Some of you have done PNM and you see Maxwell's equations. And here on the left-hand side, we have Maxwell's equations. So you have del dot E equals rho naught rho over epsilon naught. You have del dot B, which means that you have no magnetic monopoles. So this one says electric fields come from charge. This one says there's no such thing as a magnetic charge. This thing says the curl of E gives rise to magnetic fields, and similarly, the curl of B gives rise to currents and also changes in the electric field. Okay. So on the right-hand side, we have fluid equations. And we can sort of think about del dot V equals 0. So what does that mean? Del dot V. Let's write it. What is del dot V? And this is del cross V. We just said that. That's the definition of the vorticity. What is del dot V? Think about what del means again. Changes. So this is the direction of the fluid. So changes in the direction of the fluid are 0. Means that the fluid is not being, that's not being moved, right? Because you can have something left to right, that's perfectly okay. But there's no changes in the direction.
No pressure, no.
No compression, no rarefaction. So if you have an incompressible fluid, right? This is the definition of incompressible. And generally speaking, we can treat fluid like water as incompressible when it's like in our lab or in our pipes, right? So that means that we could write this del cross V as the vorticity. And if the vorticity is also 0, then we can use the potential formalism here, combining these two pieces like we would do for E and M in order to find V. Isn't that before? What? What do you mean what? Because we have this, right? Is a scalar of a potential. We use the potential formula to define V. Okay. Let's show you a little bit more. Let's talk just about a plane flow. Okay. So there is this parcel, and I have labeled all of these parts of the parcel. Here is the coordinate system, x1, x2. You can think of that as x and y if you want. 1 and 2 is perfectly fine. There is some flow in it, and the flow is changing as you move in y. So it's slower here and it's higher here. Okay, the flow is coming along, and we want to think about the deformation of this box. We'll draw it first.
Huh?
Draw it on your picture, make a little picture, before and after.
So we're trying to share the before and after.
A rectangle. What did you draw? This is the picture. Okay, how do you get bigger?
Where do you mix it?
What did you draw? Try to rotate it? Okay, what did you draw?
So I kind of pictured those videos where they put a piece of metal and they like stretch it with those hydraulic things.
Okay.
So I just kind of drew the square as a elongated rhombus.
Okay. Yeah, so let's try it together, right? So start with the bottom part here. So x1 is applied all the way down through here. So that moves it to the right. Right? B, Q, C. Now just above that, P and R, they move a little bit more. Right? So P doesn't line up above B, but it ends up over to the right. So here's P. That's not right. There's P. And R ends up even more, right? Okay. So that I can draw through there. I can draw through there. There. I can draw, right? And then at ASD, that's moving the most, right? So that's way over here. Oh, yeah, it's pretty good. pretty good draw boy, you know? Okay, so that's what you end up with. Now. Kinematics, we said early on, is connecting the motion of the fluid without describing the forces or the energies involved, right? Just how do things move. So now we have this direct connection between gradients in the velocity, changes in the velocity field, and understanding how parcels will deform, right? We haven't yet talked about how these velocity gradients are created. But what happened from here, from this box to this box on the right?
We find different ones at different spots.
Good, yes. And in the terms that we used, remember we had that box and we moved it around and we did some stuff to it? What are the different deformations that we did here?
Can we say it's rotated, but it was like tilted and squeezed?
Is it rotated?
No.
Yes, it's stressed, right? So like, what did we have here? We had a box like this, and then what happened to the edges? When they come towards one another, right? That is the definition of stress. Rotation is just, they can keep the same angle, right? When they move closer to each other, as opposed to like, a strain, for example, is two sides, the opposite sides, coming towards each other or away. When two sides that are perpendicular to one another come towards each other, those are strains, stresses, right? Okay, so this thing got stressed and it translated. Does that make sense? Okay. And of course, what we can do is we can think about what we would call the principal axes of this fluid. And we think about like a coordinate system that is written like this, right? And the deformation of the coordinate system, right? That the coordinate system would rotate, for example. Let's go with that. Okay, so that gets us almost to where we're supposed to be. So this is the homework that I would assign tonight. I'll make this live. This scary? We're going to use some of these concepts. So the first one is 3-3. And in 3-3, we're going to consider a two-dimensional flow. You compute particle trajectories, just dV, dt, dA type stuff. In 3.6, you have a two-dimensional steady flow, and it has some velocity components. And you try to show the streamlines, the components of the stress rate tensor, the rotation tensor, and the coordinate rotation that diagonalizes it. Okay. And then you can choose between 310, which is comparing the streamline, pathline, and streak line that pass through a given point. Or if you really want, you can do 314, which is determine the two different types of either unsteady or advective acceleration terms for various flows. Okay. Does that seem unreasonable? No. Okay, no one's rebelling yet. So let us pull up the next one. Where'd it go? Oh God, where'd it go? I guess we're still a tiny bit behind. We're supposed to be here. Okay. God. What? It's like a picture of a sprouting. It's not my finger, I think. Did you say a boogie? What did I put there? What? I don't remember what this was for. It's supposed to, it's something that having to do with fluid. Ignore it. I'll fix it. Okay, so we talked about this. Let's talk about another one. Okay. So what happens to this parcel as it moves along this streamline? So the flow is coming from the top and it's sort of bending at the edge of this box and it's going down. And so here I have this box here. And it starts in this orientation and it ends in this orientation. And I want you to sit just for a few seconds and really think about what's happening to this parcel. Did the parcel deform? So if I look at this parcel from point A to point B, what happened? So I think what we would say here is the first thing that happened here is compression, vertical compression, and horizontal rarefication. Right? Here it looks perfectly square, beautifully. And then this way, right? But if you didn't see those steps in between, what would you think happened? Well, what do you mean by that? What do you mean the same?
Because. You would just see the rotation.
Yeah.
Ah, so you may, depending on whether or not you're tracking the fluid, you can convince yourself that the object simply rotated. Right? That box A here and box B here, they are related through a translation, 1, 2, and a rotation. Right? And so we see, and we kind of alluded to this before, that some transformations from point A to point B can be rotations, or they can be compressions in certain ways, and they won't be able to tell the difference. Okay. Let's do one more. Here's two vortices. Okay, and I drew them sort of shittily before, and now I'm drawing them real good. So on the left-hand side, we have a parcel. And this parcel, A, B, C, D, it's going around some center object. Okay? The velocity as I change here is getting faster. What was this an example of? Yeah, it does look similar, but like what object rotates like this? The top Oreo does rotate like this, but what object did I show earlier?
Oh, a CD.
A CD plate. Because this is what you call solid body rotation. Is there deformation of this parcel? No, very good. Is the rotation of this parcel? Yes, kind of obviously, right? This is the same parcel, it's just over here, right? So there's rotation, translation as well, right? Okay. And is there vorticity? Yeah, okay, good. What about this one? What? There is deformation. Good, yeah. So the parcel didn't stay the same shape. Is the rotation? Yeah, probably. This is kind of a weird one, right? U theta is C over R. Is there vorticity? One likes yes. Who's gonna be mad if it's no? Alright, I said let's wake me up, right? Let's find out. Let's do practice. Okay? So, how do I determine the vorticity of a two-dimensional object? So I won't need this one, right? And it'll just be these two components. And let's write it out because it's a cross product, right? So it's del x. Well, I guess we should use r and theta. How do I write this? Go back to the appendix of the book. In cylindrical coordinates. By the way, here's all your identities too, if you want them. So. Here's your vorticity. This is written as del cross u. And this is in the r hat direction. 1 over r d u z del phi. Oh, shoot, we don't have any del phi. Where's the vorticity going to come out of? Which component do I have to worry about? Let's think about it. So the motion, velocity's motion is in which direction? Down. Actually, as a useful. Right, the motion of the fluid, this is the change in the velocity, but the motion of the fluid is rotational. Right, so this is actually theta. So r cross theta points where? V, 5, V, 5, pump. Which coordinate system are we using? What? Spherical.
Would we do cylindrical?
Or do we do cylindrical, right? Because there's a symmetry about the rotational axis. So in fact, this is coming out of the board. If there's vorticity, it's coming out of the board, right? Okay, so I don't want the R component, I only want the Z component. Okay. So I can ignore the other two. And according to this, it should be 1 over R d r u theta over d r minus 1 over r d u r d theta. That seems simple, right? Can you solve that for the one on the here? Oh yeah, this is C over R. This is some constant divided by R. So what's the vorticity? First, let's write what U is. U equals U R and U theta, and u z. What's UR? What? Is there motion in the direction of R? Does this parcel move in? It does? From here to here? Does it move radially? No. So UR is 0. Does it move out of the board? No. So that's 0. And what's the one in the middle? C over R. Can you solve it now? This is right on the back of the book, so I'm pretty sure I didn't do it wrong.
No.
Right, but would it be 1/c only? Because the other part cancels out, so it's 0. So it would be
Yeah,
1
no,
over
this
R.
part here is
0, right?
good. And this part here? It's also 0. Right? Because R times C over R is C, and the derivative of C with respect to R? 0. Good. So this thing has no vorticity.
Not even like a real process, how can you have something faster in the middle?
Looks like something with gravity that would happen.
Yeah, maybe. I mean, this could be a sink, right? Something sucking away the fluid in the middle here. Causing it all to rotate faster in the middle than. We don't know why the fluid is doing that. We have yet to ask the question, why did the fluid do that? Now we're only asking, how can we use these things about the fluid to understand? Okay. Good, 30 minutes. This is the type of homework that we'll do. So it's really important that you kind of have a look here and get yourself familiarized with taking the derivatives and curvilinear coordinates, whether that's spherical, whether that's cylindrical, right? That's what we're doing. And some of it you'll consider plugging and chugging, and some of it is as simple as it seems, right? So when I ask you to take the derivative, just remember, if something depends on both, you know, the position and the time, do the chain rule, right? Okay, so if you don't love derivatives, you're gonna.